Hello everyone, this is lecture 16 of PTRE 451545, Advanced Drilling. This is gonna be the review ahead of the exam that is on Thursday. We only have one exam, so make sure you study hard to do well. I will put this recording in a separate folder.
Only one this exam, that's the only exam.
Only one exam.
One on Thursday.
Yeah.
No final exam.
There is final exam. One midterm. Yeah. Yeah.
They have given he gave us the course outline by the beginning of the course. So you are aware you'll be writing final.
Yeah, otherwise it won't be at the middle of the semester.
Only one exam. Because he's talking about maybe this term is only one exam.
Yeah, one midterm. So try to do well. Don't leave any easy points on the table. It's going to be a mixture of questions. There are longer questions. There are shorter questions. This is, yeah.
How many questions are there?
It doesn't matter. I mean, so far I have, but I might change it, obviously, 5 or something. But, you know, multiple parts, 4 even. 4. But, you know, there are multiple parts. There are short, long questions, etc., etc. Oops. Yeah. I have short conceptual questions. I have longer calculation questions. Yeah. That's it, basically. You don't need to memorize any equations, but you do need to memorize, like, not memorize, but know how to apply some stuff. For instance, for pressure calculations, I'm not going to give you 0.052. I'm going to give you 0.433 and 8.33. And you need to figure out how to multiply it to get that 0.0252.
That would be a fine awarding to anybody who do that.
Well, it doesn't. Well, hopefully you are going to make it to the end of the exam. Now, I'm also not going to give you that equation like density times depth, because it's like fundamental. It's rho GH, basically. Right? I will only give you 0.433 and 8.33. You divide one by the other, you get the 0.052. I'm not going to give you 42 gallons per barrel, obviously, and 5 point, yeah. Other stuff I give you, if needed, you won't need much. But you need to know how to apply what we learn. You need to be familiar with everything that we said in class for module 1 and 2. I have one question that I think I need to change it, but the rest, kind of, the rest is okay. I might need to change one question, but to make it easier from what I have right now, but it will be easy. Just the big thing is that don't get like overwhelmed with if you see a longer hard question, make sure you get the easy points. Leave the hard points for the end, because it's okay if you don't make the long question, you don't make it fully correct, but don't lose the easy points. That's the important thing. I think all homeworks are on Blackboard. Some of you did not do very well, which was surprising, especially for homework 3, because I even said how to do it. The grades for homework 3 was 100, 100, 100, 34, 92, 93, 77, 96, 97, 67, 47, and 89 for homework 3. Homework 2, they're online. All of them, homework 2 and homework 3 should be online. So Kalu doesn't owe you anything. Now, in terms of grading, he's grading the midterm of the other class now. But yeah, I mean, you should have everything there, and yeah, you are gonna get this, and I will be uploading the project, the part A of the project, in on Thursday evening, and we are gonna go over it on Tuesday. Probably it's gonna be due next Tuesday, but you need to familiarize yourself. So I asked you guys to send email to Kalu about your pairing with for the project. It needs to be, I'm okay people doing the project by themselves, but it's not needed. You can pair up with somebody. It just needs to be from the same class. And I know that not all of you have iPhone or iPad, so one of you has to have access to the app from the two of you, and it should be okay. Then you can decide between you if you want to split the money to buy it, or you can both buy it, but you need to turn in a file with what you did. So and that will be, every part of the project is 12.5% of the grade. So it's pretty important. I think this class is 25, 25, 25, 25. So midterm is 25, final is 25, homeworks are 25, project is 25%. So, and the final exam will be comprehensive, it's the whole class into one exam. Okay, so for, if you guys have any specific questions, I can answer them. Otherwise, I can flash through the slides very quickly, trying to give you some info as we go along in regard to the exam. Any questions? Okay, so we started basic stuff about drilling, and I know some of you is your first drilling class. For undergrads, no. So it was basically, we started talking about mineral rights and leasing in the US. They are different than outside. And well, all of you guys are foreign, and myself too, and many of the people online are. So I think it needs to be, many times you see students that they come over here and they don't know this stuff. And these are important because it changes the whole way of the oil industry in the US. Is very different than outside. You don't have only state mineral ownership. You have like private, federal, Native America, etc., etc. And the rule of capture combined with
sorry, you're not sharing your screen.
Huh, Donald?
You are not sharing your screen.
Oh, sorry. You are right. Let me see. How do I share the screen? Oh, there you go. Sorry about that. There you go. Yeah. So basically, rule of capture and offset drilling rule is they came from the English common law, and basically they accelerated drilling in the US, and because drilling was accelerated, technology accelerated, and therefore became basically the oil and gas industries. They say it's the most American thing, even more American than the computer science business. 2/3 of the rights, of the mineral rights of the US are privately owned. You can have multiple owners. That made the leasing, basically the process of leasing, very complicated. And you have the landowners, you have the surface owners, you have the royalty interest holders, etc., etc. You have landmen trying to do the in-between negotiations, they get a cut. You have the lease brokers, successful landmen become lease brokers. And then you have the lease, which has to deal with conveyance, term, and royalty. There is a lot of clauses on a lease, just like when you sign up to rent an apartment. There is a lot of clauses. You have to keep it clean. You have to not leave trash outside, etc., etc. Same thing here. From the lease, you have the granting clause, consideration, land description, and then weird clauses. Some of them have weird names because of how they were initiated, and it's so on and so forth. Obviously, don't memorize all this stuff. Execution of the lease is if you are a drilling contractor or the operator, you will, or the operator may lease a drilling contractor. You are responsible for exploration, permits, acquirement, and development. Actually, you will be the operator if you are responsible for the exploration, permits acquisition, and development, because then you might hire a drilling contractor to do the drilling for you. But if you are a drilling contractor in general, you are not going to be responsible for all this. You are responsible for the drilling, but operator cares about everything: the production, completion, etc., etc. Now, if you are going to leave, you have to farm out. You need to find somebody to take your lease with the current terms. This is a big thing in petroleum engineering, leasing. You have to farm out, so you have the farmer and the farmee. The farmee farms in, the farmer farms out. Three kinds of well types, 4 kinds of contract. It's really 3 kinds of contract. The 4th one came up the last few decades, really. Well, it's 4 now, but yeah, it used to be 3 main ones. Actually, post-Iraq war, service contracts became very, very common. So, well, shale revolution kind of timeline. We have day work, you pay by day. Footage, you pay by foot drill. Turnkey, you pay for the entire thing. Service contract, you pay for the whole project, in a sense. That's why turnkey and service contract is very similar, but service contract is like it's specific to the clauses of the contract. Is more like turnkey, you pay for the whole project, the entire job. Service contract is really it depends on what the contract says. Somebody else is going to do the job for you, a specific job for you. It can be the whole thing, it can be part of the thing, etc., etc. Now, this is between the operator and the drilling contractor. You are a company that has rigs. The contractor will hire you to do under these contracts to drill him some wells. Drilling abroad has different kinds of contracts. It's really 4, and then the 5th one is combination of the other 4. Concession is the most common. PSA, production sharing agreement, joint venture, service contract. That's basically a company from the US or a company from one country going to another country to drill. And you have the IOCs and the NOCs. This is important to know the difference between the two because of the weird naming. Because in the US, a public company is a company that is traded in the stock market. So you have Exxon, you have Shell, you have BP, you have Chevron, you have basically those IOCs, international oil companies. And then anywhere outside the US, when you say a public company, it's an NOC. It's a company that belongs to the state, like CNPC, Chinese National Petroleum Company, Pemex, PDVSA, Equinor, Petrobras, etc., etc. So they are both called public companies. One is publicly traded, the other one is publicly owned. The ones that are publicly traded, they don't belong to somebody, they belong to everyone. You can go online and buy stocks right now of ExxonMobil. Then automatically you own a small, tiny percentage of ExxonMobil, right? Belongs to everyone. Doesn't belong, it can't belong to anyone. Whereas NOCs belongs to the government, at least big part. Equinor is mixed. I think it's 20%. Saudi Aramco is 95%, something like that. Anyway, and then you have this important slide with the systems of the rig. You have power, you have hoisting, you have rotating, you have circulating, you have well control. Everything, rigs looks different from each other, but they all have these 5 functions in one form or another. And we made the analogy with cars. Any car you look at, it's basically, it will have the same functions. Same thing with every rig. This is how it looks like, schematic. And then modern day drilling rig, I gave you a schematic with a lot of components. Just if you are looking for something specific, you can look, but of course it's not like ideal. It's not like there are things on rigs that you don't see in this picture, and things that are not on some rigs that you see in this picture. The goal is to drill a hole on the earth and from which to recover hydrocarbons, and do it at least, go deeper, cheaper, right? Go as deep as you can, as cheap as you can. The rigs, they have typical personnel names: tool pusher, driller, derrickman, roughnecks, roustabouts. Tool pusher is the leader of the rig crew. So if you are a drilling contractor, you have rigs, you probably have a couple of tool pushers for every rig. So one changes, the shift changes every 2 weeks. So one tool pusher comes with one crew, one leaves, goes home, argues with his wife, comes back 2 weeks later. Then you have the driller, who's basically he's an experienced guy. Sometimes there is an assistant driller who is about to become a driller, and a senior driller, let's say. Or the assistant driller is the junior driller. You have the derrickman, which is an experienced, the most experienced roughneck, most likely. And then the roughnecks, they just started. I don't know how long you can stay being a roughneck. It's probably the hardest job out there. One of the hardest jobs in the world, probably. Roustabout is a young, not very specialized crew member. Maybe he's painting dog houses or something like that. Not very, you don't need training to be a roustabout. If they say roustabout job, they mean a job that you don't need to be trained to do. But this is not exclusive, at least. You have the mud engineer, you have the people who are working for the mud engineer hands, you have the mud logger, you have the directional driller, you have the geosteerer, you have a bunch of people that are not here. In offshore, you have even more. You have the offshore installation manager, who replaces the tool pusher. You have additional marine crew, seamen, which are responsible for the rig, additional maintenance staff, catering people, etc., etc.
Why,
Yeah.
why did they decide to use the name OIM instead of tool pusher offshore?
That's a good question. I don't know the answer to that. Offshore installation manager. I guess it has to do with history. Probably they used it the first time in Sky. I don't know. But this is the head of the crew offshore, offshore installation manager. Then you are preparing the drill site, you are drilling, you are making a cellar. The cellar is gonna hold the basically the substructure. The substructure is gonna hold the substructure together, but the substructure goes above the cellar, right? This is the whole substructure. It's the bottom of the substructure, this, and then the rest is that. Basically, what you see above the cellar is basically the blowout preventer. Back then, when we went over it, we didn't know yet the blowout preventer, so I didn't mention it in the slide. But now you know that this is the blowout preventer. As you see, angular ram, shear or blind or pipe rams, etc., etc. And this is the bottom of the BOP, the base. Yeah, sometimes you use a different rig to drill the first portion of the well, which is where the conductor casing would be. You prepare the drill site, you rig up, and then you are ready, you spud in, you drill a mouse hole, you drill a rat hole, mouse hole fits the next joint, rat hole fits the Kelly when it's not drilling. Spudding has to do with potato. It's basically dropping a potato. Spud is the what happens when the potato hits the ground, let's say. It's from the old days of cable tool drilling, when they were releasing the bit the first time to hit the bottom. It was called spudding. We are ready to spud. That's nowadays when we say this well spudded on that date, it means that we started drilling on that day for this well. Rigging up. Derrick. We said that the derrick got his name from Thomas Derrick, who was an executioner in Britain. He ended up being hanged himself with a derrick. Or no, he hung. I think so. He hung whoever made him an executioner. He ended up hanging him as well. He hung a lot of people. And he was very. They were calling Derrick anyone who was any executioner. The name was called Derrick. Anyway, rigging up involves other stuff, auxiliary equipment, like involving for supplying electricity, water, compressed air. You need this stuff on the rig, as you know. Storage facilities and living quarters for the crew. We call that man camp. And supplies like tubulars for the job. Spudding in. When you start rotating, you're basically making hole. The word making hole, it means that we are drilling, actively drilling. You start with a big bit and then you go smaller, smaller, smaller as you go down. You run casing, you cement, as you know now. Yeah, spudding in or spudding. Every now and then, well, predetermined stages on the drilling process, you stop drilling, you retrieve the bit, and you run casing, and then you cement. And you wait for the cement to set, and then you go in with a smaller bit, you go deeper. The bottom of the casing, every casing string is called the casing shoe, and that's the most vulnerable point to fracturing. So casing shoe depth is very important. The power system, that's what we started looking at, is like, how do you supply power in the rig, which needs a lot of power. Offshore, you need even more power because you also need to keep the vessel in place, etc., etc. You have ordinary diesel engines, but more fancy stuff as well, like LPG engines, or even natural gas engines. And we have seen in our last field trip at Williston, we saw a rig that was on highline, basically an electric rig. Engines are very important because without it, it's like the heart of the rig. Without it, nothing on the rig works. So you have to have them protected and maintained very well. The transmission, this is an important slide, is made in two primary ways, mechanical drive and electric drive. Mechanical drive is older version. You basically have to transmit motion. So you need to align stuff a certain way. You have compounds, they have shears and pulleys and stuff and gears, and you have them lined up to transmit motion from the engines to the stuff on the rig, like the drawworks and the, what else is taking a lot? Mud pumps. Nowadays, you use electric transmission most of the time. And you have the SCR house, which is basically a gigantic transformer that you go from DC AC current created by the engines to DC current, what everything is using, basically. This is how the SCR looks like. SCR house, very well cooled. And then you have the hoisting system, which is basically to lift up the drill string, which is very, very heavy, very, very heavy. You have a system that is called block and tackle, which is what we see here. And we do a lot about it in the first class. We do like fleet body diagram on it, etc., etc. But basically, it goes from the drawworks up to the crown block, down to the anchor. And the anchor grabs the drill line and doesn't let it move. Every now and then you need to do this process of slip and cut. Slip and cut. You move it a little bit and you cut it, so you apply stress elsewhere. So you don't apply stress at the same place every time, and then you're gonna like be done with it. Crown block, the number of lines sprung are important, as we saw in the previous class. And you have attached the drilling hook, and from the drilling hook you have basically it's a hook, you can lift anything you want. One important thing, the right line on the left that is attached to the draw collars, sorry, to the drawworks, what am I saying? Drawworks is moving, we call it the fast line, and the other line that is attached to the deadline anchor, or the anchor is basically called the deadline because it's not moving. Crown block is not moving, traveling block is moving. So deadline and crown block are not moving. Traveling block and fast line are moving. Drawers are huge. They take a lot of energy. You have the pipe rack where you store the pipe, you number it accordingly. And you have to move the pipe rack accordingly so that it doesn't get bent by the wind, depending on the forecast. You have slips that are important. They are being put in the hole so that they can hold the drill pipe without having to lift it. They hold it in place. They have dies basically welded on. the slips. No, I don't weld it. They are, no, they are, you need to replace them every now and then because they basically deform. They catch the drill string from falling in. It's like this. These are slips, right? I'm holding it, right? Otherwise, it will fall. Okay. Now, when the slips are holding the drill string, they apply stress on it. They cause deformities. That means you need to replace this stuff every now and then. You have generally three pairs of slips in every rig. Onshore. Offshore, you have more. The circulating system, this is not a very accurate schematic. You don't go from the shale shaker to the degasser necessarily. Sometimes you have degasser before the shale shaker or after the shale shaker. But basically the way they did it went from heavy particles to smaller. By the way, you suck mud from the mud tank, you put it into the mud from the mud tank to the mud pump to the suction line, discharge at high pressure from the discharge line, standpipe, rotary hose, swivel, wash pipe on the swivel. Swivel does the rotate. Everything below it does rotate. Below it is the Kelly. Below that is the drill string. Actually, the Kelly is considered part of the drill string. Drill string has drill pipe, drill collars, the bottom hole assembly basically, and bead. And after that, it comes out from the annulus, generally at atmospheric pressure, and then you go through the return line down to the system that will clean it up. The degasser, shale shaker, desander, desilter, etc., etc. Some gaseous fancy formats, they have rotating head here, which doesn't let gas escape, which forces it to go through the bluey line, where it's either flared or put into a tank, closed tank, of course. Some pictures. Functions of the drilling mud are important. Most important ones, the primary ones, is pressure control and cuttings transport to the surface. The rest are secondary: maintain wellbore stability, prevent formation damage, cool and lubricate the drill string, provide information about the wellbore, act as a barrier, protection barrier to personnel, equipment in the environment. I want you to know this stuff. The rotating system is, okay, how do you rotate? There are two ways. The old-fashioned way is the rotary table. The newer-fashioned way is the top drive. Nowadays in Williston, I don't think you have a single rotary table, Rick. You have in Permian. Drill string is drill pipe, bottom hole assembly, and bead. This is how the rotary table works. Basically, rotation is provided from the rig floor. You have the turntable which rotates. This is what you rotate. Inside it, you have the master bushing. Inside it, you have the Kelly drive bushing. Then you have the Kelly saver sub. Sub basically means going from one profile to another profile. And then inside is the Kelly. So the turntable basically rotates the Kelly. The Kellys are attached to the swivel, so everything below the swivel is rotating. Okay, and then the whole drill string, including the Kelly, is rotating. I dropped a goldfish. What is it? Rotary table main components. We talk about Kelly. It's either 40 or 54 feet long. And then you have the top drive, which is basically a fancy swivel which rotates. Okay, it's made to rotate. So the rotation is no longer from the turntable, but from the swivel. So the swivel is made to do as much of the functions as possible. We call it the top drive. And this is how they look today, most of the rigs. They are bigger structures. There are some advantages, some disadvantages between the top drive and the Kelly rigs. Top drives are more expensive and they have a bigger footprint, but they are safer, faster, make directional drilling easier and more efficient. The bit, a lot of stories about the bit. The roller cone bit, it was invented by Howard Hughes, which made him a lot of money. When oil companies did not have a lot of money, he was making money. And his son at one point was the richest guy in the world. Then came the drag bits, and we have the fixed cutter, drag bit, PVC bit, is one example of fixed cutter bit. It depends on what you are drilling. Then we have the more fancy bits like the fishtail and the hybrid bit. Hybrid bit was very efficient when you have thin layer formations, thin layers, and you go from soft to hard, soft to hard. So when you are in the hard formation, you like to use fixed cutter. When you are in the soft, you like to use roller cone. And you are you don't have the layers are very thin. It's not worth it pulling out of the hole to change the bit. So that's where you use Chimera. Chimera was very, very fancy. A lot of people wanted to try it. After drilling, you stop drilling. You decide what are you gonna do with the hole that you drill. Is it good? Are we gonna complete it and go for production, or are we gonna plug and abandon? These days you have a lot of holes from the same pad. And then you need to case and cement. Several kinds of casing: conductor, surface, intermediate, and production. Some people don't consider conductor as a casing string. That's why Schlag SLB here calls it pipe. But where conductor pipe, most of the times people call it conductor casing. But so it's like you have conductor casing, surface casing, intermediate casing, production casing, right? Casing is different from liners in a sense that liners don't go up to the surface, but casing does tie to the wellhead. You have the Halliburton Red Book that can give you any information about the casing available, liners, tubulars in general. Cementing is very important. Needs to be done a certain way. If it's not done a certain way, you are in trouble. It makes it easier for you to get in trouble. You can do it in the wrong way, in a skip part, and get it right. But when you don't get it right, it's very hard to fix. Most of the cementing, the original part of the cementing job is called primary cementing, and any remedial one is going to be called secondary cementing, like squeeze cementing or remedial cementing. Some equipment that is used is the casing shoe or the guide shoe, centralizers, float collars, the bottom plug, the top plug, and they need to go a certain way. And they need to all be used. If you skip something, again, like I said earlier, you make it easy for you to have a failure. Bottom plug will go in first, and it's gonna be red or orange, and the top plug black or yellow will go after. And those are rubber, made of rubber. They are very easy to drill through. But the first one, the bottom plug, can break very easily. It has a diaphragm, and you apply pressure above a certain value, and then it breaks. The top plug, it won't break. It's made to transmit pressure. So it won't break. If you get the mix, you're going to be in trouble. You're going to have a whole well full of cement that you have to drill through. Basically, you have to do drilling again. Float collar, very drillable. Casing shoe, very drillable. Who invented the casing shoe was Reuben C. Baker, 1907. Cementing, we use Portland cement. Portland cement is not only used for oil wells, it's used for other stuff too. But the most common classes that we are using is A, B, C, G, H. Actually, I was in Colorado School of Mines for spring break. I went to my old office and I saw some postdocs there, and they were telling me that they are using a kind of cement for construction site that is 90% magnesium oxide. It becomes pink when you hydrate it. And it's pretty strong. In oil and gas, we like expansive cements. There is reason for that. We like cements that when they cure, they expand. They create some sort of favorable situation in terms of well integrity. You don't want leakages from the reservoir to the surface or the seafloor. But these are the classes that we are using. And this is a picture from PetroWiki, which is now in One Pedro. SP didn't have money to keep its PetroWiki page. It had to move it to One Pedro. So they have one page for everything, basically. It's just like the way I had in the same website with JPT. It was around nighttime when they did the change. But anyway, these are some additives that you can use. It's not an exhaustive list, but this is the main list from the Petroleum Engineering Handbook. You have API gravity. That was the first equation that we saw in the class. Very important equation. Basically, it goes the opposite of density. If the density is high, API is low. If the density is low, API is high. What is the density of fresh water? Is 10 degrees API. For reference, West Texas Intermediate is 39.6 on average. And then you have, when you are dealing with gas, I need to tell you what to use, basically. Because gas is very different. Several empirical correlations are helping with the situation. And then we had the mud window, which is very important because it shows you where your mud weight needs to be. It cannot be smaller than the pore pressure. It cannot be larger than the fractional gradient. You need to stay there, okay, in between. If you are in the lower than the pore pressure, you get a kick. If you are above the fractional pressure, you get a fracture, no circulation, and then a kick. Two ways you can do casing design, bottom up or top down. We did it both ways. Bottom up is up to the left. Top down is down to the right. But in real life, it's not just pore pressure and fractional pressure. you have the older students, the graduate students have seen in other classes, like geomechanics and well conditions, but the undergrads will see next year. When we say fractional pressure, it's a lot of numbers, and you need to choose the smallest one of them. And pore pressure is not just pore pressure. Sometimes it's what we call the breakout pressure, which is a little bit higher than the pore pressure. You need to choose obviously the maximum of that because it's a lower bound. But also these mud weights, these mud windows that we talk about, and the whole module 1, in all honesty, was about static considerations. Module 2 was about moving, dynamic analysis. This is how to do the casing selection. You have a clearance ratio rule of thumb. I don't want you to memorize it. And then the most important thing in this module was the YouTube model. The way we model our wellbore based on a YouTube is very important. On the top left, on the left leg is the drill pipe side. On the right is the annulus side. On the top of the left is the drill pipe pressure. On the top of the right leg is the casing pressure. At the bottom of the YouTube is BHP. Underneath the YouTube is the formation pore pressure. And you can correlate it to various portions of the circulation system. You need to know how to use the YouTube model. And this is the most important equation, which I'm not going to give you. I'm only going to give you 0.433, 8.33. You need to be able to use this equation. Okay? It's rho GH, basically. Okay? How much the hydrostatic depth, pressure of a fluid is at a given depth, or the hydrostatic pressure gradient. You should be able, like, if I give you density and depth, you give me pressure. If I give you density and pressure, you can give me depth. If I give you depth and pressure, you give me density, etc. You need to be very, very comfortable with this stuff. Example, blah, blah, blah. Now, offshore, you also need to care about the weight of the sea above you. Those are static pressure loads. When you have the well shut in, the surface pressures are building up to a point where the BHP would be equal to the FPP. When you shut in the well, because you have a kick or something, you force BHP to become equal to the FPP by adding those pressures. Okay, so those pressures are very useful because they can tell you what you are missing basically on each side. And in one side, if you have two fluids, you are missing different on the other side. And this is something, it's an operations-based class, as I said many times. So think about it. You are in the field, you are shadowing a drilling engineer, and you have a kick. What is he going to give you? He's going to give you SIDPP and SICP. And then you need to do some assumptions, some data manipulation, some calculations, simple calculations based on the YouTube model to figure out, oh, this is probably my kick density, this is probably my kick height, this is the D fluid tool, this is the TV, this is the, yeah, I mean, very easy. Same thing with the exam. I mean, it won't be very, 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 very applied, I would say. What does it mean when SICP is not the same as SIDPP? We talk about it a lot. It means that you have different fluids on each side or different aggregate fluid density on each side. Static fluid levels, we saw them in homework 1. They are a concept. If the static fluid level is on the surface, you're probably missing mud weight. Your mud weight is not high enough. The blowout prevention system, I didn't go through it tremendously well because we're going to have a whole module on it, module 4. Talk about basically I had to introduce what is the blowout preventer here. Wellheads, you have dry tree or wet tree. Offshore is wet tree at the sea floor, dry tree on the rig. Obviously, advantages and disadvantages of both. You prefer to have it dry so that you can access it. Otherwise, you need a ROV to access it, a remote operating vehicle. Different BOP ramps, has an angular. And then you have blind shear pipe ram. I will show the next slide. And then you have the kill line where you inject in and the choke line where you produce from, or you get out of the circulator out from. Stripping is the act of moving a pipe down with a closed BOP. The BOP needs to satisfy the following functions. And it's going to be used to shut in the well, basically, when you lose control of it, or you thought you lost control of it. This is about the BOP. Then we talk about offshore drilling, Mr. Charlie, modern day offshore drilling operations, different modus. Modus is what you are going to use, a module, mobile offshore drilling unit, you are going to use to drill an exploratory well, maybe an appraisal well, but you are really not going to use it for development wells. Development wells are drilled when you really know that area very well. And you're not going to go fancy with that, okay? Submersibles, posted barges, bottle type submersible, Arctic submersible, barge for a marsh, drilling in a marsh area, in the marshlands, or a swamp, disgusting waters. Jackups, stable, movable. Jackups are a very successful invention. Very, very successful, very, very practical invention. Inland barges. I see these pictures and I remember Louisiana. Drill ships are the most cutting edge technology it goes to. That's as deep as you can go. That's as, it's like as high tech as you can go. Thrusters to keep it in place. Semi-subs, not very stable. And then we saw, well, still jagged platforms. No, drilling platforms is what you are going to use to drill mostly a development well. They are larger. They are actually intended to become production platforms. They are going to start from drilling, and then they are going to drill a bunch of wells, and they are going to eventually become, after modification, to a production facility. So they are bigger. They are in areas where you have knowledge, good knowledge so far, and you have been planning their installation for 15 years or something. The average well offshore, it requires 7-year plan to be drilled before it starts drilling.
7 years.
Yeah, 7 years. These are even more because you have drilled the exploration well, you have drilled several appraisal wells, you know you have came up with a development plan, you studied which development plan works best, and then you go in there. Now you are certain of your plan, you are confident in your plan, you put your money on the plan.
And it takes 7 years.
On average. I remember reading
What
that
if,
in
because
2017.
your economists must have done your economics, your MPV,
Yeah,
what
yeah,
if the oil price changes the structure?
Of course, there is a lot of. That's why when the oil price changes, there are still. When the oil price drops, there are projects still going on, right? Because they were planned before. Yeah. And there are some that are halted. I mean, yeah, it's long-term contracts on average. I remember reading that in 2015, actually. I don't know if it changed now. Somebody mentioned it. I have a good memory. I remember it was a PTRE meeting, and one of the sophomores said that he checked online, and he said that on average, the an offshore well requires 7 years of planning or something. I don't know what it is nowadays, but I mean, I don't think it's very quick. We have rigid platforms and compliant platforms. Rigid platforms are more rigid. Compliant platforms are more compliant. We have steel jagged platforms, concrete gravity platform, saison type platform. That's a lot of cement. A lot of cement. And then you have GUI tower platform, tension leg platform, and spar platform. This is a picture of, I forgot from where. It's being, you understand it's a huge structure, and it's gonna have a more permanent sort of use. This is a lot of cement, crazy amount of cement. And then you have the steel saison K-zone platform, which is basically reinforced steel so that it can handle the friction with the ice, which is very, very bad. Very bad. Friction with ice is worse than friction with water, obviously. It's almost as bad as friction with sand. Spar platform. Yeah, that was the end of module 1. This is what we learned from module 1, which was long. And now module 2, which was shorter, but more mathematical. It was drilling hydraulics. But could keep an eye when they show up. I would carry on until they show up. I hope they don't show up. Yeah. Huh? Yeah. So what we learned about the circulation system, this is what was focused on module 2. We broke down the circulation system into different components, and we said that if I go with the flow of mud, okay, I need to keep subtracting friction. I don't care if the mud flows the way I'm doing my calculations, friction is always against the flow, okay, no matter what. But when it comes to pressure, hydrostatic pressure, if I gain depth, I have more fluid above me, I need to be adding. So yes, I'm subtracting from friction, but I'm also adding from depth as I go down. And then when I come up from the annulus, I'm subtracting through to friction, and I'm also subtracting with hydrostatic because I have less and less fluid above me. Now on the surface, I don't care about depth differences or height differences on the surface. I assume it's negligible, but I do have friction on the surface, right? I have friction everywhere. And they should all add up to this equation. This is how you use the YouTube model for. And then we came up, because now we have friction, we have dynamic mud weight values, which are different than the static mud weight. We learn about, and this is important, equivalent mud weight and equivalent circulating density. You had a whole homework on that. Very hard to calculate frictional losses, very, very hard in so many fluid flow through and large equipment. Sorry. And we learn about the hydraulic loop, and I drew it wrong the first time. I remember I was part of it. I didn't draw it right. So we start from here. We lose pressure from friction on the surface. Then we go down. Then steeper gradient because more friction, same loss per foot, same mud weight, more friction. So smaller value of PSI per foot gain net, bigger gradient feet per PSI. Then I ignore the height of the bead because it's tiny. I lose this pressure on the bead, jet nozzles of the bead. Then I go up through the here, the annulus between the BHA and the borehole, and then back up to 0. And if I am studying and I'm not moving, automatically I am like this. That was what I drew wrong the first time, remember? The other thing I did wrong, I said wrong in class, is that I said that the top drive only puts one joint at a time. It can do that, but it can also drill one stand at a time. The Kelly is what goes one joint at a time.
Yeah, that's what you're saying.
Yeah, and then I corrected myself. I made a mistake the first time I mentioned it. But yeah, now that I remember, I didn't mention it on module 1, but yeah, so that's why the top drive is taller, is 100 feet. Anyway, that's the hydraulic loop. I want you to know how to use the hydraulic loop in a sense that, as we said, every point on the hydraulic loop has a depth and a pressure value, right? Every point on the hydraulic loop has a depth, has a depth and a pressure. Some points have depth and two pressures. So it's like here, look, I have this pressure here, it's somewhere here. And this pressure here, which is, sorry, I did it the other way around. This one is here, inside. This one is here, outside. So if I ask you for the EMW here, you are gonna give me one EMW here and one EMW here. Same depth, inside the drill pipe and outside the drill pipe, right?
But if you are specific, what is the EMW in that loss?
Yeah,
Just
but
give one.
if I give you EMW at 3,000 feet depth, you need to give me two values. Okay, it's very different because it's very important. Each side has a different. You look at each side for different perspective. ECD is the. I need to draw it again. ECD is a special kind of. Okay. I'm drawing it backwards, but I didn't draw it excellently. Okay, it's better if I draw it. Okay, this is one, and then this is the static. Okay, now ECD is a very special kind of EMW. Is the EMW here, this point here, right after the bead, and generally is with the bead at the bottom, rotating, blah blah blah. ECD. ECD is a value of EMW. It's a special value of EMW. I know people like using it interchangeably. And my advanced drilling professor didn't like that either because it confuses people. They are all density values, but remember, density and total depth, you can always convert pressure and depth to a density equivalent and vice versa. This is the official equation for ECD. You need to know how much would be the frictional losses on the annulus. And this is the official equation of EMW, really. If the bit is touching the bottom, TVD bit is equal to TVD total. So ECD is basically equal to EMW at that point, which is the official definition of ECD. And this is an equation that if you need, I'm gonna give you, okay? But I think you should know how to use it. To get anywhere on the hydraulic loop, you can get the EMW, right? And you don't really need the hydraulic loop most of the time. You can draw the hydraulic loop, sketch it very fast, but sometimes you don't need it. If you know the pressure at that point and the depth, automatically make it EMW. Very easy. If the bit is not touching the bottom, it may be easier to subtract all pressure losses to friction from DPP or add anything left to CP. You can go anyway. But if you go against the flow, you need to be adding frictional losses. If you go against the flow in your calculations. Sample problem, video, surgeon swap. When you put pipe into the well, the pressure goes up. You need to be careful for fracturing. When you pull out of the hole, pressure goes down. You need to be afraid of getting a kick. Modern rigs can accommodate that. If you accommodate that, you're able to be fast when you are putting pipe in the well or pipe out, and you make a lot of money. A lot of technology dedicated to these tasks. Bit hydraulics optimization, two ways. Either maximize the hydraulic horsepower at the bit or maximize the bit's jet impact force. This is the two ways, those are important. Not applicable when you have downhole motor. Maximizing the horsepower at the bit requires bigger pressure losses across the bit. And maximizing the jet impact force requires less. Some derivations that you don't need to know. Oh, sorry, equations here. These are important. If you need to use them, I will give them to you. Drilling fluid rheology. We talked about different rheology types. Are they waiting?
I've not seen anybody.
Maybe they're still enjoying a spring break.
I hope so.
Yeah.
Yeah. Rheology is a big topic. It has to do with the way the fluid behaves, how much motion you get from the stress you apply, basically. We have the viscosity, we have the yield point. This is how it looks on a plot. We talk about Newtonian fluids. When you see the word Newtonian, always think of linearity, okay? Something called linear. Normal behavior, like very, very linear behavior. Water, glycerin, big hand plastic is like toothpaste. You need to apply some stress and then you get motion. And after that, it's more like Newtonian. Power law is very, very, it's bending. It can be, what is it? We said shear thinning or shear thickening, etc., etc. We use some other words too. Herschel-Buckley is very common for oil-based, for drilling mats, oil-based mat in particular. It's like big hand plastic, sorry, power law with yield strength. So it's basically these two combined together for Herschel-Buckley. Very, very common in the oil field. Very, very common in the oil field. This is the derivation. I don't want you to know the derivation, but I do want you to know this concept, which is what you use on your homework 3. Yeah, this part I don't want you to know. It's good to know this. But if you have to use it, I will give it to you. Now, this is the other way. Sorry, no, this is not the other way. This is basically for optimal flow rate. This is the other way, maximizing jet impact force. I actually made a mistake here. I told you guys that if you look at the Rabia's book, which was 1986, not 1978, you will find the derivation. No, it wasn't there. I downloaded the book, it wasn't there. It was just the results. The derivation is in a paper called Robinson, written by Robinson in 1982. Yeah, if you want to see the derivation is long and mathematically tedious. Obviously, I don't want you to know it for the exam, but just saying, if you want the derivation, since I messed it up when I told you the wrong.
So if we are to use that optimum flow, use all these equations
Oh. Yeah. 1982. I'm not gonna give you basically this first one. This first two, I'm not gonna give you this because this is something that you need to know. But I'll give you anything else. Those weird stuff, weird numbers, don't need to memorize them. Okay, I think, okay, we use rheometer in the lab, some approximation, some correlation. We use Marsh funnel on the field so that we don't break it. Problems, mud balance, routine pipe calculations. Actually, most of you have seen them before. I think only Roxon is the first time that he's seeing it because you guys took well completions or advanced simulations, and the undergrads have taken drilling with me. So these are generally important equations. And oh, this is another. I'm not gonna give you this 1029.4 because it's a very important value that you need to know. Very important conversion factor. This is a modified version of the same equation. Sometimes ID is not given, and sometimes you are not sure about ID because you have a lot of ODs with the same ID, with different ID, same OD, different ID. Tubulars, and you may not be very confident, and you may not have a vernier calipers to measure it. So this is another equation you can use. Variations, hole cleaning. Hole cleaning is all about Stokes' law, which is Stokes' law of settling. It's how fast you can bring the cuttings to the surface before they sink. In water, they sink fast. So you have some viscosifiers like lignosulfates to build viscosity in your mud. This is a very easy calculation, but it's very hard to get like a good average density of the solids and stuff. It's very simple equation, very hard to implement. A lot of stuff. Porosity is not constant. ROP is not constant. Bunch of stuff. So when we are drilling, independent parameters, pump rate, rotational speed, weight on the bead, mud weight, and rheology. And I want to put also here mud in. And then dynamic dependent measurements is drill pipe pressure, casing pressure, rate of penetration. These are the results of what you are inputting. Mud flow out, mud flow out, and active pit volume. Mechanical specific energy, you want it as low as possible. That's the energy you need to remove 1 kilogram of rock. Then how you make a connection, talk about it here. Round trip, how it's done. When do you stop drilling? When you made it. When you have differential sticking, we basically cannot drill anymore. When you have low circulation and anything out of ordinary, or if you take a kick, and then what is taking a kick? Kick indicators, I want you to know them. Okay, kick indicators, and the videos that we watched, and that was it. Thank you very much. Good luck in your exam. Today office hours is 12 to 3. If there is people still at 3 o'clock waiting, I will extend to 4. So yeah, and good luck. Bring calculator in the exam. Ruler, you don't need ruler, but you can have one. Scratch paper if you want. Yeah. Anyway, thank you everyone. Good luck in the exam. And I'm available by email if you need me, and outside of the office hours, and also the TA. Stop recording.